we're going to start with looking at this first transition here, which is a 5 electron volt photon. So we need to convert that into an energy and then a wavelength. So the first thing is the energy of that photon would be HF, which is hc over lambda. So the wavelength is going to be hc over E. And we can convert the 5 electron volts into joules because the equation here, this energy needs to be in joules. So 5 electron volts is 5 times 1.6 times 10 to the minus 19 joules. So from that equation, if I shove that information in, I get 248. Well, I get 2.48 times 10 to the minus 7 meters, which is this wavelength. So we've definitely got that first wavelength accounted for. The next thing is to look at what's missing, which is this wavelength here. So I'm going to take a little bit of a shortcut. If I multiply the first wavelength times 5, that will get me to roughly the second wavelength. Yeah, that's pretty close. So if the wavelength is multiplying by 5, this tells me that the energy is dividing by 5. So we go from 5 electron volts to 1 electron volt. So this infrared photon here, this is a 1 electron volt photon. Now, the only way for that to be emitted from this atom is for the top energy level here to be minus 4 electron volts, so that there's then a difference of 1 electron volt when it jumps down. The final spectral line, if I make a bit of space now, is from the top energy level all the way down to the bottom. So that's going to be this jump here. And that's going to be 6 electron volts. So with an energy of 6 electron volts, remember that's 6 times 1.6 times 10 to the minus 19 joules. If I put that into this equation here, that gives me 2.07 times 10 to the minus 7 meters, or 207 nanometers.